We'll start with just some background information, and then we'll kind of dive into the details as we go. So what we're really talking about when we talk about PTR-TOF, or the Vocus ion source, is chemical analysis by mass spectrometry. And so what we mean by this is converting a neutral molecule, let's say in the air, into an ion that can be measured by a mass spectrometer. And so in order for a mass spectrometer to work, we need to charge neutrals, and then we'll measure their mass to charge ratio. Proton transfer reaction, or PTR, is one type of chemical ionization method that we can ionize lots of different types of compounds with in a very quantitative and controlled manner. So where are we going in this webinar? We're going to be talking specifically about the Vocus PTR-TOF, which is a new ion source developed by Tofwerk. And this is going to combine three important technologies. So the Vocus ion source and reactor, a high-performance atmospheric pressure interface TOF platform, and then a suite of acquisition and analysis software, which allows you to efficiently analyze your data. And so the result of all these three things coming together is that, as we'll show, is that we'll present market-leading sensitivity and speed, the ability to separate isobars in a complex mixture with high mass resolving power, and a robust instrument that you can take in the field or you can run in the lab. And we'll introduce some workflows in terms of data analysis processes to give you a feel for how you analyze data that you collect with this instrument. So the first thing is, whenever you're going to make a measurement, is to select the right mass analyzer. So traditionally, PTR-MSs were originally developed with quadrupole mass spectrometers. And now more recently, and specifically with the Vocus, we use a time-of-flight mass analyzer. So let's just look at a couple important details of these different mass analyzers. So you can think of a quadrupole as a selector. And so you can only measure one mass at a time because all other masses are discarded. So if you have a complex mixture and you need to measure lots of different masses all at the same time, a quadrupole will be very slow, and it will also be very hard to separate different compounds which have the same nominal mass, so isobars, because quadrupoles typically have unit mass resolution. A TOF you can think of more of like a sorter. So if we have an incoming mixed ion population, we will give them a fixed amount of energy and shoot them across a set distance and measure their time of flight by measuring their arrival times. And so in this way, we can acquire an entire mass spectrum at the same time, because as we pulse these ions through the mass spectrometer, they'll separate and we'll measure them all very quickly. So we can do this whole process very, very fast, so more than 40,000 times per second. And in this way, we can get a very high sensitivity, so our duty cycle is quite high. But the main advantages of TOF, aside from measuring the whole mass spectrum at the same time, is that they have high enough mass resolution and to measure or to assign elemental formulas to the ions that you detect. And we'll look at some examples as we go through this presentation. For those of you who are not familiar with Tofwerk, Tofwerk is a global provider of TOF technology. Tofwerk's delivered over 400 mass spectrometers around the world and supports a host of different OEM, custom, and research designs of mass spectrometers. So this includes ion mobility mass spectrometers, GC TOF interfaces, electron impact TOFs, and what we're talking about today, the Vocus PTR-TOF. Tofwerk is a small company, which is a huge advantage when you're talking about specific applications and customized instruments. And it's also has quite a long history in atmospheric research with its partner Aerodyne in the United States. And the idea of Tofwerk is really to bring laboratory performance into difficult to measure environments. So whether that's the field, aircraft, tall towers, etc. This is where Tofwerk's strength lies. A little bit of history about the PTR-TOF at Tofwerk. So in 2002, the world's first PTR-TOF was put together with the University of Innsbruck. And this coupled a Tofwerk time-of-flight mass spectrometer with the drift tube developed at the University of Innsbruck. And shortly thereafter, Tofwerk and Ionicon became partners in delivering PTR-TOFs around the world. So Tofwerk served as an OEM provider of TOF technology, and Tofwerk focused mostly on developments of new interfaces to improve the sensitivity and resolution of PTR-TOF instruments. So for example, the quadrupole interface TOF was developed at Tofwerk. In 2017, so very recently, this partnership came to an end when Ionicon released a new product line without Tofwerk TOFs. And shortly thereafter, Tofwerk patented and the Vocus ion source and reactor, and launched the Vocus PTR-TOF with its product line of time-of-flight analyzers. So for those of you who are not familiar with the kind of core Tofwerk technologies, this is one of the core Tofwerk technologies, which is called the API-TOF, so Atmospheric Pressure Interface TOF. And it's compatible with lots of different ion sources, including the Vocus. It's been deployed around the world on every continent, even in Antarctica, high up on mountaintops, on ships and airplanes. So it's a compact and robust platform to make measurements from. And it's played a key role in many scientific publications, even in Nature and Science. So it's the foundation on which the Vocus is built. So in order to start talking about the Vocus, we need to start first by talking about PTRMS and proton transfer reactions and how they proceed. So if we want to measure in the atmosphere a VOC termed R, the goal here is to react H3O plus ions, so hydronium ions, with neutral molecules R to protonate R and make an adduct. And this is then the proton transfer. So the rate at which this proceeds depends a lot on the water cluster distribution and what your primary ion looks like. So this forward reaction will only happen if the proton affinity of the molecule you want to detect is higher than that of your reactant ions. So if your reactant ions are H3O+, they have a proton affinity of water, then you can ionize things like benzene, methanol, toluene, as well as DMS, benzoic acid, MBK. But if you have too much water, or your water cluster distribution is not controlled, and you're fixed with the first water cluster, so that means H3O+ with a water attached, then your ability to ionize things like benzene or formaldehyde or acetic acid or formic acid falls off quite steeply because the proton transfer reaction does not proceed. And so depending on how you configure your instrument, you can operate, for example, with only H3O+ ions, and then ionize a large suite of molecules. But there are some important compounds that we do not ionize, like propane is an example of something that has a proton affinity less than that of water. So even if you just have H3O+ in your reactor, you'll be unable to ionize that type of molecule. So how does this actually work? So this is a schematic of a conventional PTR drift tube. So on the left, we have water vapor inlet, which feeds a glow discharge, a hollow cathode source. This is basically a plasma that makes ions. And then ions are pushed and electrostatically pulled into a reactor. This reactor is at low pressure, so typically 1 to 3 millibar. And along the drift tube region, ions get pulled by an electric field across the reactor. And as they do that, they can collide with neutral molecules, or they can just diffuse and basically spread out in this drift tube while they react. So your analyte inlet comes in from the side, and here they basically mix and are accelerated this way. And the way they're accelerated is by an electric field. So the drift tube is constructed of a series of metal rings separated by isolators and connected by resistors so that we can generate a linear electric field along the length of the reactor. So this electric field in the axial direction or along the length of the reactor is how we control the cluster distribution of the primary ions, so how much water is attached to your hydronium ions. And this is basically the main control knob over a PTRMS in terms of what it will ionize and how sensitively it will do that. as you can see by these red lines, as ions go down the tube, down the reactor, they spread, and that's, again, the combined effects of diffusion and scattering. So at the end, where there's an orifice, only a small amount will actually make it into the mass analyzer. So there's basically a target, and if you're not in the middle of the target or near the target, you will not enter the mass spectrometer. And those are then ions lost. So the Vocus concept is actually quite simple. Quadrupoles have been used quite a lot to focus ions into a nice beam. And so our idea is basically, could we use this quadrupole principle with a conventional reactor to kind of take the best of both worlds? The quadrupole could help keep ions away from the wall and make sure that they get through the sampling orifice at the end of the reactor. And the drift principle is quite nice because it gives you controlled reaction conditions, and it's a low pressure system, so the pumping requirements are quite low. And so this idea is basically, let's take the best of both worlds and try to make a reactor. And the problem is that while this idea is good, it's not possible with a traditional reactor. And this is because the quadrupolar field will not penetrate metal rings. So metal is a really good shield. And so if you try to pass a quadrupole field through a stacked ring electrode, like is in a regular PTR drift cell, then the RF just doesn't go in, and so the effect doesn't work. So it's not possible with a conventional reactor design, and so that's where we started to think a little bit harder about how we could actually make this work. And the way we came up with was to use a resistive glass tube. So in the schematic in the top, this is the orange part. And by using a resistive glass tube, we can choose the resistance to be high enough that the RF field can pass through, but the resistance is also low enough that we can still generate an electric field between the two ends. So instead of a resistor chain of metal electrodes, we just have a resistive coating. And this allows us to generate a linear axial field in the same way that you would normally do, but also superimpose this quadrupole field around it, so we pull ions into the middle of the reactor. So this schematic here is quite hand-wavy. This is not actually what it looks like. So we can actually look at, in a more quantitative sense of what happens inside this reactor and these two fields by using SimIon to model it. And this is what it looks like. So here, the gray line is the schematic of the walls of the reactor. And we inject ions on the left here. And then we let them fly across the tube in this direction and aim for the exit orifice on the right. So ions are traveling from the left to the right. The black lines are the DC field only. And what you see is ions start in a packet here and get scattered as they go this way. And very few of them actually make it out the orifice. Some of them hit the wall, some of them hit the side wall, but the sampling efficiency at the end is very low. Then if we take the exact same geometry and we just superimpose an RF field on top of that, so this would be the quadrupolar field from the Vocus, then the same ion initial positions are shown on the left in red. And you can see that the beam is focused quite efficiently into the exit orifice. So we lose virtually none of these product ions when they transit the reactor. And so by increasing the efficiency at which they come out, we directly improve the sensitivity of the instrument because more ions are going to enter the mass spectrometer. So coupling an ion source to a mass spectrometer is not a small feat. Here I'm showing you a schematic of the Tofwerk instruments. Here we have the Vocus ion source. This is operated at 1 to 3 millibar. It's fed into a differentially pumped region, so with a quadrupole ion guide. So we have a quadrupole to focus and pump away the neutrals. Then they enter a primary beam lens stack. And then this is the TOF part, where they come out of the extractor and they are pulsed, and they travel a V mode path to a detector. And by traveling a fixed distance and measuring the time of flight very accurately, we basically measure the mass. In the bottom, I'm showing you two different flight paths. The blue one is for a HTOF, or a standard Vocus instrument. And then the Vocus 2R has a longer flight path, and that's denoted by the red, and that gives you more resolution, which we'll talk about in a little bit more detail in a moment. So the efficiency with which you leave the reactor is one constraint on your sensitivity. So if you don't make it out of the reactor efficiently, you'll have a low sensitivity. But similarly, if you get out of the reactor but you don't make it into the TOF efficiently, then you will also have a similarly low sensitivity. And so by combining these two quadrupole fields, using the Vocus RF field and the quadrupole field to basically remove the neutrals and pool the ions as they go into the TOF, we're able to make this overall process very efficient. And then in the front, for the Vocus, the interface to your sample, for example, if you're trying to measure air, like in environmental science, you might have something like a laminar core or a core sampling inlet where you pull a huge flow and you just take off the little flow from the middle. Or if you have a different application where you're looking at very sticky things from a low flow system, you might use a heated transfer capillary. Or if you have lots of different samples like in biology or something like that, you can connect the same source to an autosampler and measure lots of different things with the same instrument. So what does this actually look like? This is a picture of the Vocus 2R. We'll start on the right. So the whole instrument is enclosed in these shielding metal plates, so that you're not influenced by interference from cell phones or radios or things like that. Then you have this inlet flange here, which is shown again here. This is where your sample axis or your sample inlet axis is. And then we have a bypass pump because this is configured for atmospheric measurements. Inside the case, what you have is here a swage lock connection to your sample tube. And then the resistive glass tube starts in this peak and extends into the instrument on axis. Then we have the water vapor input port here, which feeds the ion source. And then a multi-purpose zero and calibrate port, which comes in the side of the sample inlet there. And the point is, depending on your application, you might not use a swage lock connection, you might use a capillary or something else. But the common flange here is used in all the couplings. So you just get a different flange, but the same reactor for all applications. So if we go back to some real data, first we need to remember this proton affinity rule about what we can ionize. So here I've highlighted benzene, which is in the black box. We're going to look at benzene as a function of the Vocus properties and how we ionize it. So if we want to ionize benzene, we need to remember that the first water cluster, so H3O plus clustered with one water, won't ionize benzene efficiently, if at all. And instead we want to use just H3O plus, the bare ion. So for that, we're going to need to apply some electric fields to make sure that the cluster distribution in the reactor is what we want it to be. So first, let's look at the water vapor cluster distribution in the reactor. So I'll just walk you through this color map. On the right, you see the color bar. This is the fraction of total reagent ions. Then on the right panel is the N equals 2 water cluster. In the middle is the first water cluster. And on the left is just H3O plus. So because the selectivity and sensitivity depend on the cluster distribution in the reaction cell, this is kind of the ionization efficiency, we want to understand how these different parameters affect that. So on the y-axis is the RF amplitude. So this is kind of the superimposed focusing field. And on the x-axis is the DC field, so the traditional axial field, which accelerates ions down the tube. And the point of this graph is that most of these colors are aligned in the vertical. So if I look at H3O plus, these are basically vertical lines with some little bit of slope. And same in the first water cluster, they're mostly organized along the vertical. And what that means is that the primary way that you're going to control your water cluster distribution is the same way you used to in a regular drift tube, and it's with this axial gradient. So this DC field that pulls ions along the tube. And that the RF then has a secondary effect. So the lines aren't perfectly straight, but they're very straight on average. So the way you control the water cluster distribution is, again, with a DC field. So now we can look at a little bit more detail about the combination of these for a product ion. So something that we would like to ionize, like benzene. So here's a similar color map. So the RF amplitude on the y-axis, and on the x-axis, the DC field or the axial gradient. So if we take a section along the top, so with the RF on across a axial gradient, that's what's shown in the top plot. And we see very low sensitivity at low axial fields, and then increasing sensitivity and starting to plateau as you get to higher electric fields. This is basically because benzene will only react with H3O+. So now I've put on the same plot the H3O+ signal in blue and the H2O clustered with H3O+, so the first water cluster. And what you can see is that the sensitivity to benzene follows very closely the fraction of the primary ions that are contained in H3O+. So if you wanted to ionize benzene just from the chemical standpoint, then you would want to run it at a high electric field in the axial direction. Then if we look on the side panel here, going up along this magenta line is going across in this direction, and that's increasing the RF amplitude. So we're turning up the focusing voltage, and this makes a huge difference in the overall sensitivity of benzene. So on the order of 100 times. So if you look on the lower right panel, here's the RF off, and this is increasing the RF voltage, and you get, as you go up, and you get to, well, in this case, unit efficiency relative to the maximum. So it's 2 orders of magnitude better sampling efficiency at the end of the reactor, and that's directly related to sensitivity improvement. So that's just one compound. We can look at lots of different compounds, and we can compare to kind of a conventional PTR-MS. So based on what I just showed you, you would expect that we're much more sensitive than a conventional PTR using just a drift tube by the addition of this RF focusing field. And so these, on the x-axis in this plot, are the sensitivity in counts per second per ppb from a publication from the NOAA H3O+ TOF. So it's a PTR-TOF similar to a QI interface. And on the x-axis is the sensitivity of the Vocus in counts per second per ppb. So the first thing that's important in this plot is that these compounds basically have a linear relationship between the two instruments, which means that the reaction conditions that are running in the two instruments are similar. So we have a similar response to a conventional reaction tube. But the second most important thing is that the slope is roughly 30. So that means compared to a conventional drift tube, we have about 30 times more sensitivity. And that's quite important if you're looking at low concentrations or fast processes. So this is comparing to one drift tube that's kind of a state-of-the-art instrument. If we take a step back and compare this to kind of the big picture in terms of the PTR-TOF landscapes, this is a similar plot but also as a function of resolving power. So on the x-axis, we have resolving power, and this is basically how well you can separate isobars. That's a linear scale. And then on the y-axis, we have the sensitivity in counts per second per ppb on a log scale. And so the conventional PTR-MS instruments are in this range in blue, and these sensitivities are taken from a review paper, which you can find here. And then plotted on the same graph are the 3 Vocus configurations. So one on the upper left, the Vocus C. This is the compact instrument with a resolution of 1,200. Then the Vocus standard, which has a resolving power of 5,000, and the Vocus 2R, which has a resolving power of 12,000 and up to 15,000. So you can kind of see the landscape of PTR-TOFs available. And the important thing here is that we have higher sensitivity in all models. And also the Vocus 2R is really pushing the resolution to a new limit or a new level. So what does this actually mean? What does this high sensitivity actually mean if you want to make a measurement? So it means that you're able to detect lower concentrations faster. So we're able to detect parts per trillion concentrations in seconds in parts of the mass spectrum. So in this graph, what I'm showing you is 2 different time domains. One is 1 second measurements, and one is 1 minute measurements. So the 1 seconds are in gray, and the 1 minute in red. So what I've done here is measured clean air for like 30 minutes. then I take 3 times the standard deviation of the background measurements, which is clean air, and then assume the benzene sensitivity for the whole mass spectrum. And so that gives me then a picture of what kind of detection limits I would expect across the full mass spectrum. At the low end of the mass scale, here we have higher on average LODs, and this comes from the fact that at low mass, it's more likely that you have a background. So, for example, benzene is very hard to get completely rid of. And so for benzene, you'll have more background than you would something at high mass, let's say out in the 350 range, where there you're most likely going to be counting statistics limited. So depending on, so if you have a low background, then you're just looking at basically electronic noise, and the sensitivity there really helps because you'll sooner see a peak than you would with lower sensitivity. So if we look at some real world examples then, we can look at a comparison now, a side-by-side comparison with the NOAA instrument, so the H3O plus SIMS. And this data comes from Karsten Warnecke and Joost de Gouw and Abby Koss, who made measurements with the Vocus side-by-side with their measured instrument in Boulder, Colorado. And here we can see very quickly, so the NOAA instrument is in red and the Vocus instrument is in black. For concentrations that are high, on the order of a few ppb, like toluene, the agreement is really quantitative, but also the noise level is not so much better with the Vocus. I mean, it's better, but it's not going to completely change the way you interpret your time series. But as we go to lower and lower concentrations, going down from the C8 aromatics to the C9 to the C10, for low concentrations where you're limited by sensitivity, you can see that the Vocus is very precise and its signal to noise is very good even at 1 second. So if you're trying to measure low concentrations quickly, then this improved sensitivity is very important. So as I mentioned before, the Vocus 2R, so the highest resolution instrument we have, is a big jump forwards in resolution, which means that you can resolve things and quantify things more robustly. So on the right, I'm showing you part of a mass spectrum from the Netherlands during Actress Intercomparison campaign. And what you see in red is the observed spectrum by the 2R instrument. And so you can see there are multiple different compounds present at this nominal mass. And then what we've done is we've taken this real mass spectrum that we measured with 12,000 resolution, and we've downsampled it to simulate what it would look like with different instruments. So in blue, we show the same spectrum with a resolution of 5,000 and with a resolution of 1,200. And for complex samples, like air in the Netherlands, this extra resolving power going up to 12,000 really makes a big difference if you want to quantify individual ions. So for example, this composition here would be very difficult to resolve with 5,000 resolution, and this peak here would be near impossible to separate and quantify. So if you're looking at really complex samples, this added resolution can be very quite useful. We can also look at different examples than not just air. So here what I've done in the lab is just measured with a 2R instrument again and cut a single pine needle in front of the inlet. And you can see this mass spectrum that is produced in the bottom panel. And then I've just taken a little section at 111 and blown it up so you can see that it's not just air in the Netherlands that is complicated. Almost all samples that we measure have very distinct features when you zoom in. And resolving these features is really a question of resolution. So for complicated samples, this resolution is quite important. The time response of the Vocus is also quite good. So if you want to measure very fast processes at low concentrations, then the combination of sensitivity and fast time response is very important. So this is measurements from the Netherlands. In blue is xylene, and in red, monoterpenes. So this is late fall, so basically everything is dead. But what we can see are these high-frequency spikes in xylene. And what I can do is then zoom in. So this is zooming into a region over here. And what you can see is that the noise is actually very, very low in the measurement. And the time response is actually very good. So these are measurements made at 2 hertz. And we're quite easily able to measure things kind of in the 20 bpt range with very little noise, and then very fast time response for these localized plumes which come through the site. So this kind of high frequency measurement is basically exactly what fluxes are made from. And so this type of instrument with high sensitivity would be ideal for fast processes like eddy covariance fluxes, even at low absolute concentrations. During actress, we are able to run the instrument in ambient air side by side with lots of instruments. And part of the routine measurement using the Vocus is to calibrate it with an internal calibration standard. So here what I'm showing is 3 days of additions to the inlet of different compounds from a certified calibration cylinder. And what you can see is that the reproducibility of the instrument is very good. So this is added to air that has changing water vapor and these sorts of things. And still, over 3 days, we have relative standard deviations in the calibration to these different compounds of on the order of 5%. And because we track the instrument calibration regularly when we're making long-term measurements, then it's the absolute precision is actually even better than that, because this is across 3 days, and we calibrate more frequently than 3 days. So just to look at dynamic range a little bit, here's a separate example, not atmospheric science related, that highlights the dynamic range of the instrument. So in the time series here at t equals 0, I eat a Ricola, and before and after, I'm just repeatedly breathing into the instrument. So you can see on the left here, my exhale-inhale cycle plotted with isoprene. You can see this very rhythmic pattern as I breathe into the instrument. And then here, compounds like sesquiterpenes, monoterpenes, menthol acetate, which are in Ricola drops, come up quite quickly and start to follow the same rhythmic pattern as I breathe out. The importance of sesquiterpenes and monoterpenes in Ricola are not particularly important for what we're discussing, but what is important is the dynamic range. So that's the range in concentration which we can measure. So again, at 3 hertz in this case. So if we count the orders of magnitude going up here, it's 6 order of magnitude dynamic range. So we're able to measure things in the PPT concentration and all the way up to hundreds of ppb. So many orders of magnitude at high time resolution. So making measurements and instrument stats are very important when you're trying to decide how to make a measurement or what instrument you should use. But equally important is kind of how easy it is to look at your data. Because even if you could collect great data, it requires post-processing. And this is a very important part of the analysis process. So just to kind of walk you through what this kind of workflow looks like, basically you would start the instrument and optimize it, optimize the voltages and the tuning for your specific application. And so we'll cover this software called Thuner. Then while you're acquiring your data, you would use a software called Equality, which provides full instrument control, automation and sequencing. So for example, background measurements and calibrations, and also give you a real-time way to look at your data. And then you would step into the final software package, which is Tofware, and there you'll be able to do averaging, mass calibration, look at instrument parameters, for example, resolution and peak shape, perform peak identification and assignment, and then generate time series of the data of interest. So we'll just kind of walk through this workflow. So the first thing you would need to do is optimize your instrument for the target compound. So let's say you wanted to optimize to alpha-pinene, you could set up Thuner, which is a piece of software that comes with the Vocus, to optimize the instrument voltages and tuning to optimize the sensitivity of this compound. And it's a quite powerful piece of software for mapping out the parameter space you have to operate in. So each one of these dots is a separate combination of voltages that Thuner has tested. And you could choose to run at reduced resolution and high sensitivity, or you could say, well, for my application, the concentrations will be quite high. I would instead like to trade off some sensitivity for resolution and move your way along this curve and operate at higher than quoted resolution. Similarly, if you're just starting up the instrument after a long time, or you have a new optimum that you want to check, you can very quickly, on the order of a few minutes, make sure that your instrument is optimized for your measurement by just clicking a sequence and waiting about 5 minutes, and it will generate a plot like this. So if you were detuned, it would first optimize the top voltages and improve the resolution, and then improve the interface and take you back to an optimum that you would want to run at. So the point is that you don't need to be a mass spectrometry expert to have an instrument that's running at peak performance. Then Ability is a user interface like you see on the right here in the screenshot. You have control of your voltages in the voltage tab, a time series and mass spectrum panel. And here you can also control sequences, for example, zero valves, calibration valves. And you can also customize this interface to different people or to different applications. So if you share one instrument in a lab that does different things, you can have basically all your preferences set up in this software, so it's quick to get running when you have time on the instrument. Then Tofware is kind of the post-processing part of the data analysis system. And here I'm showing you an example of the mass accuracy window. So on the left, you have the mass accuracy panel. So here you identify compounds that you know in the mass spectrum and use these to build a robust conversion from ion time of flight to mass to charge. And you can do this actually quite robustly. So here's an example over 2 hours of the mass accuracy at mass 45, which shows a standard deviation of 0.8 ppm or 0.000036 Thomson. So we can measure these masses quite accurately, and that's very important for doing later steps where you want to identify unknowns in your mass spectrum. And this is all a graphical user interface, which is quite easy to use, even if you don't have a lot of mass spectrometry background. Then as you dive deeper into the kind of post-processing workflow, you need to define a couple of other instrument functions. So this includes determining the resolution, which is done in a couple of clicks. You can see the resolution function plotted in the bottom panel here. This instrument was reaching resolutions of 12,000. And here you can see the peak shape function. So this is the kind of non-ideal flight properties. So if in a perfect world, it would be a Gaussian distribution, but it's not a perfect world. So you have sometimes tails and things like that. But here you can see this instrument was tuned to 12,000 resolution with nearly a Gaussian peak shape, which is plotted here. And so this is all kind of put into a GUI so that you can graphically determine the peak shape, determine the resolution, and be on your way for fitting. So then the final part of the post-processing workflow is to do the high-resolution fitting. So here I'm showing you a spectrum that I've already shown you before, which is measured with 12,000 resolution on the 2R from the Netherlands. And the peak fitting and peak identification process is basically taking these different bumps and fitting them with peak shape corrected peaks, and then taking the center, so using the mass accuracy of the instrument to identify possible elemental compositions, and then selecting these and fitting the high resolution time series. And so this is all done in a graphical interface with kind of a predefined workflow so that you can step through your analysis efficiently. So then just to kind of summarize what I've showed you today. So the Vocus itself is a novel ion source and reactor, which is coupled then to a kind of established existing time of flight mass spectrometer from Tofware. The Vocus is equally suited to the lab or the field because the time of flight mass spectrometers we use are specifically designed for these different environments. And then what the Vocus can provide for your measurements is very high sensitivities, which mean better level of detections, better precision, and higher speed when you're measuring low concentrations. Then the 2R instrument has a quite high resolution resolving power, so 12,000 to 15,000. And this is really important if you're looking at complex mixtures and you need to separate different isomers, which I showed some examples of. And then the workflow in the post-processing and the instrument setup is meant to be kind of a straightforward process that you don't need to be an expert to get high quality data out of the instrument. So with that, we'll end, and if there are questions, then I think Joel can field them. But thanks for your attention.
Yeah, thank you very much, Felipe. And just as a reminder, if you do want to ask a question, on the bottom of your screen, you should see a Q&A button where you can type in questions, and then I can relay these in the order they come in. There was one question midway through, as I think you were showing a couple of different examples. Someone was asking if there are any publications yet on this instrument or anything available.
There's a manuscript in preparation, but it is, should be submitted soon, but it is not yet published. And as participants in the actress inner comparison, there's also a manuscript that will be prepared from that, comparing 12 different PTRMSs, all in the same place at the same time with the same standards. So that publication will also be coming out hopefully soon.
The next question is related to the sensitivity in the different models. It says, how is it possible that all of the models have the same sensitivity regardless of the TOF used? Shouldn't they be different for longer or shorter TOFs?
Yeah, so the interface is the same and the ion source is the same. And once you get to the TOF, the losses of ions in the H-TOF and the L-TOF, the two different mass analyzers, are not significantly different. So you will achieve the same sensitivities in the two instruments. So if I go back to the interface schematic, well, actually we can start here. So all of these different instruments have very different interfaces. So the QI-TOF has a very similar interface to what we use because we designed it. And so this has a quadrupole interface, whereas these other ones have a lens stack, and the lens is much less efficient at transmitting ions. And then this instrument has a hexapole combined with an ion funnel. And so anyway, all these different instruments have different interfaces, and we all have the same interface, just different TOFs. And that's why all the sensitivities are the same.
Will there be, someone's asking if there'll be an instrument at AGU, and I believe the answer is no. Aerodyne will be at the AGU, if plenty of people there representing Aerodyne will be available to chat for sure. Question coming, and sorry, there's a couple I'm reading at the same time, so let me just sort through these. Do you offer the users are ready to choose? Oh, okay. So there's a question about, do you offer the RF and DC voltage combination to the user? And I think if I understand the question, they're saying, do you allow the user to do the adjustment to choose between the H3O plus or the water cluster as the main reagent ion? So is that an adjustable setting? Yeah, so basically this color map I'm showing you again here, this voltage is controllable by the user, and as is this voltage. So you can choose any point on this graph that you want to run. And you can also, I showed you an example for benzene, but if you're interested in a different molecule, you could make a similar graph and then choose the optimum that you choose. So yeah, both of these are controllable parameters, and you can choose any range of these voltages that you want. Next question has to do with formaldehyde, and just in particular, is there any experience measuring formaldehyde with this instrument yet?
Yeah, so formaldehyde is quite tricky with PTRMS in general. And in our instrument, we have quite a lot of absolute water. So from the way we generate our ions, we have a high absolute amount of water, and formaldehyde can do backwards reactions when you have high water vapor concentrations. And so formaldehyde is a very tricky one that we haven't looked super carefully in detail with. We've been working mostly more with the kind of benzene, toluene, xylene mixture, and then biogenic hydrocarbons and things like that. So compounds like formaldehyde will be very tricky still, but have not been investigated in detail yet.
Okay. Well, I'm just going to hold off here one more second. Hope there's another question rolling in. Sorry. Have you run it with NO plus primary ions?
So yeah, we've generated NO plus, but we have not done a as thorough calibration basis set, but we generate a lot of NO plus ions. And as we get more standards at Tofwerk, then we'll present more about the calibration to NO plus. But you would expect similarly high sensitivities relative to other instruments, basically because this effect is general. It doesn't matter which reagent ion you use. This focusing effect will be general to anything you make from the ion source. So in that way, you would expect similarly high sensitivity. But stay tuned for absolute numbers.
Okay, well, I think, unless something rolls in here in the next couple of seconds, I think that is it for the questions. And we do want to thank everybody again for joining us. And you should feel free to follow up